So now I'm ready to examine the relationship between players' intelligence and their behavior. Okay? And in game theory, players are trying to maximize their payoff, and the payoffs are often given by a payoff table, and you see those numbers 3, 2, and 0. And I'm going to explain exactly what those numbers mean. That's the starting point in examining the relationship between intelligence of players and the outcome. Okay, so what are the payoffs in a game? Those numbers 3, 2, and 0. Well, they may be prize or profit. So $3, $2, $0. That's one possibility. Or it may represent benefits in some sense of the player or the level of satisfaction. Okay? So the concept of payoff is not so clear. What those numbers represent is not so clear. So let me give you precise explanation what those numbers are or what those numbers should be. Okay, so there are two cases. One is easier case, the other is a harder case. The easier case concerns the situation where there is no uncertainty. Okay, so let me explain what I mean by a situation without any uncertainty. So the situation I'm thinking about now has no random events. So nothing like weather or stock price is present in the game. So no random events in the game, and no random behavior in the game. So unlike the game of rock, paper, and scissors, people are not taking random strategies. Okay? So when there is no uncertainty, it's very easy to specify players' payoffs. In this situation without any uncertainty, to determine a player's payoff, it's very easy. You can just assign larger numbers for better outcomes. The better the outcome, the larger the number. That's your payoff. So let me explain what I mean by a very simple example. Let's suppose the game has 3 outcomes: best outcome, worst outcome, and worst outcome for you. Okay? And your task is to assign payoff to this outcome, payoff to the middle outcome, and payoff to the worst outcome. Well, you can assign larger number for better outcome. So one way is 3 for best, 2 for the middle, and 1 for the worst. Okay? Larger numbers for better outcomes. This is one possibility. But there are lots of other possible ways of assigning payoffs. Well, this is another way, 100, 8, and minus 1. And this is still another way, 20, 19, and 0. Okay? So game theory says any one of those choices is fine. Okay, so, and let me explain why. So any assignment of numbers is fine as long as you assign larger numbers for better outcomes. Why? So no matter which representation or which choice you choose, let's suppose 20, 19, and 0, that is one way to assign larger numbers for better outcome. Okay, so maximizing your payoff means choosing better behavior. Okay? It really doesn't depend on whether this number is 20 or 100. As long as this number here is larger than this number, and as long as this number is larger than this number, payoff maximization means choosing better outcome. Okay? Okay, so to determine players' payoff in a situation without any uncertainty, you can just assign larger numbers to better outcomes for the player. Okay, so that is how you should specify payoffs in a game when there is no uncertainty. Okay, suppose you have some uncertainty in the game. Then you should assign payoffs more carefully. So let me explain how I do that. Okay, so let's consider a situation with uncertainty. So maybe there are some random events like weather or stock price in the game. Or maybe people are taking random behavior like rock, paper, and scissors. So in that kind of situation, player may like risk, or players may dislike risk. And you have to somehow represent those two different situations. Okay? So let's suppose you have a random event in a game, and suppose a player is facing a choice between a lottery and some other outcome. So if a player chooses a lottery, with probability 1/2, he gets $10, and with the other probability 1/2, he gets 0. So uncertain event, the outcome of the lottery is here. So this is one choice, choosing this lottery. Another choice, the other choice is to get $5 for sure. Okay, so let's examine what is best for you. There is no right answer. It really depends on how you like or dislike the risk. Okay, so if you choose this lottery here, on average, you can get $5. Okay, so half the time you get $10, half the time you get 0. On average, you get $5. This is the expected payment of this lottery. On the other hand, if you take the other choice, you get $5 for sure. So on average, those two choices give you exactly the same amount. What's the difference? Well, difference is obvious. Lottery has some risk, and this choice here doesn't have any risk. It's a safe choice. So if you like risk, if you are a gambler, it's more fun to play this lottery, so you may choose risky choice. Okay, so risk-loving people, gamblers, may choose this lottery. But if you are conservative or cautious, you may like the other choice, safe choice. So risk-averse players choose the second choice. Okay, so we have to represent those two different behaviors somehow, and here is a very easy way. Okay. First, you assume that players get some utility from outcome. Okay, so if you choose this lottery, outcome would be either $10 or $0. So you get some utility out of $10. Okay, and if outcome is $0, you get some utility of $0. Okay, so with equal probability, you either get this utility or that utility. And if you choose the other alternative, you get this utility coming from $5 for sure. Okay? And then, after assigning those numbers, utilities, you should assume that players are maximizing expected utility. Okay? So if player chooses this lottery, half of the time, he gets utility from $10, U of 10, and half of the time, he gets utility coming from $0. So on average, his satisfaction or expected utility is this one. On the other hand, if a player chooses the other alternative, he gets $5 for sure. So he gets satisfaction or utility from $5 for sure. Okay? So if number here is smaller than the average of satisfaction of 10 and 0, so if $5 for sure have small utility, then you choose lottery because lottery has larger expected utility. Okay? And if your utility from $5 for sure is larger compared to the average of utility of 10 and 0, and then this is better for you. Okay? And you choose $5 for sure. Okay, so let me sum up. Okay? So when uncertainty is present in game situation, a player's payoff is equal to utility coming from the outcome, and you assume that players are maximizing expected utility. Okay? And by specifying those numbers, utilities coming from outcomes, you can describe if a player likes or dislikes the risk.